Okay, so this is 12.2a. It's really not too horribly hard. I know anytime anybody sees a sigma, it's like, this is going to be the worst thing in the world. But it's not too horrible, and I'm going to say it's easier than the last time you had to use sigma notation. So hopefully that's encouraging. It is kind of long, so try not to get lost in these huge, long math sentences. But besides that, it's not too horrible. Okay, so I'm first going to start out by writing our YP. So this is the general format of what we assume the particular solution of a Fourier series type problem looks like. So we have A naught over 2 plus the summation n equals 1 to infinity of a sub n cosine pi n x, and then plus the summation b sub n sine pi n x. And that should look familiar because you needed to use it in the last problem on your exam. So, I mean the first problem on your exam. Okay, so we're actually going to solve this very similarly to your last test on power series approximations, or reflections, or whatever you want to call them. Okay, so the first step is we're going to find our y double prime, which means we have to find our y prime to begin with. So to get our y prime, we're just going to differentiate like normal. So this is just a constant. I know that may be a little bit confusing because it has so many different things going on with the a's and the n's and the negative ones and all that crazy stuff, but keep in mind that all this stuff here is just a constant as well. These are constant values, and x is your only changing variable in these problems. So keep that in mind when you're differentiating. Okay, so your y prime is going to equal your negative sigma n equals 1 to infinity of n pi a sub naught, a sub n, and then times your sine I in x. We're going to differentiate the next term similarly, and we're going to get n equals 1 to infinity of our n pi a sub naught cosine I n x. Okay, so that is our first derivative. Now we need our second one. So you get your negative here, n equals 1. Our sine's going to turn back into a cosine, so we have our n squared, our pi squared here, thanks to the chain rule. We still have our a sub n cosine pi n x. Okay, and now this term is going to be negative infinity for n squared pi squared b sub n sine pi n x. Okay, so now we have all of our derivatives, and we can start plugging in all these values. Okay, so it's really long, and I actually had to turn my paper sideways to fit it all, so I'm really hoping I can squeeze it all on one line here to avoid any extra confusion that doesn't need to be involved. Okay, so we have our y double prime. So I'm actually going to scoot it over as far as I possibly can because I really don't know if I can fit it. Okay, summation n equals 1 for n squared pi squared a sub n cosine pi n x minus our sine term here, n squared pi squared b sub n sine x or pi n x. Okay, so that's our y double prime term. Now we need our y term. So we have our a sub naught over 2 plus our summation from n to 0, from n equals 1 to infinity, a sub n cosine pi n x plus summation n equals 1 to infinity, b sub n sine pi n x. Okay, and like I thought, it doesn't quite fit, but that's okay because this is all equal to our f of x here. So maybe I can fit at least that bit in. Okay, so we know it's all equal to our f of x. So the next step is we're going to combine as much as we can. So we're going to, since all are summations, that's actually really nice about this problem, is the last time you had to deal with series representations of a solution, it was hard because you had to re-index and all that crazy stuff, but your indexes are already set up and that's really, really nice. So it's not quite as difficult as it was the last time you had to do it. So we're gonna combine as much as we possibly can. So we're gonna get our sines and our cosines together. So actually I'm gonna start with our a sub naught over 2. Okay, and now let's start with our cosines. So here we have an a sub naught cosine with no coefficient, a sub n, I'm sorry, or a sub n cosine with no coefficient. So if we were going to factor your a sub n, your cosine term out, you'd be left with a positive 1. Okay, and then for our next cosine term over here, we have a negative n squared pi squared for our coefficient, and then we can pull out an a sub n, and then our cosine term, pi n x. Okay, and so we're going to do the same exact thing for our sine term. So we're going to have plus our summation equals 1 to infinity. And it actually is almost the exact same thing because we have our positive sine term over here with no coefficient other than the b sub n. So we have a positive 1, and then minus our n squared pi squared times our b sub n sine n pi x. Okay, and so now we've condensed as much as we can, and I'm going to set it equal to our f of x over here. Actually, I don't think I'm going to fit it, and it's going to make it look sloppy. So we're just going to reference it up here. Okay, so I like to think about it like this. Looking at this, do you see any sine terms? Do you see any sine terms in your Fourier series? No. So there's nothing that your b sub n could equal that's going to make this sine term a cosine term. That's not how numbers work. So we know that our b sub n has to be 0 because we have no sine terms on this side of the equation. So b sub n has to equal 0. Okay, and what about lone standing constants? Do you see anything like that? No. So our a sub naught is also equal to 0. Move this down. Okay. So now with this knowledge, we can set this part of the equation equal to our f of x. So when you do that, get something that looks like this: 1 minus n squared pi squared a sub n cosine pi n x, and then equals our summation, it equals 1 to infinity 1 minus negative 1n, n squared, pi squared, cosine n pi x. Okay, and now you can treat it like any other equation. So we have a cosine on both sides, so we can cross those out. Okay, and we have a summation, so those are gone too. So now all you have is this term, and we're trying to solve for our coefficients here. We're trying to solve for all of these. Okay, so now all you really need to do is to divide by this right here to isolate your a sub n. Okay, so you get your a sub n is equal to what you already had, 1 minus your negative 1 to the n squared, pi squared, and then the whole thing has been divided by 1 minus n squared pi squared. Okay, and those are actually all your coefficients. So hopefully that wasn't as hard as you thought it was going to be. Let me know if you have any questions whatsoever. I really like this test. I know it's a little more labor intensive algebraically, but it is really, really interesting, and I hope you guys like it. I guess let me know if you have any questions.